Welcome to engineering measurement course. So in the last few classes we are discussing about a civil engineering application of Matlab. So using Matlab software, basically we are writing few civil engineering basic experiments and we are implementing it. So in the previous classes, that is lecture number 7, we have discussed basics about Matlab, that is stresses, strains, how to compute that, all these things we have discussed. Then in experiment number 8, we have discussed about how to compute the bending moment diagram of a beam. Because as a civil engineer, we have to design a beam, design the columns. So for designing the beams and columns, we need to find it out the shear force and bending moment diagrams of a beam. So that's what we did in the last experiment. That is, we have find it out the bending moment diagrams and bending moments at the different location of the beam using simply concentrated load. So in this experiment, that is experiment 9, we will be calculating the computation of shear force using the MATLAB. So as I discussed in the last lecture also, these are the typical types of beams normally is available in reality, like cantilever beam. When one side of the beam is fixed and other side of the beam is free, then we call it as a cantilever type beam. Then we have simply supported beam, means a beam is simply resting on two supports, that we call it simply supported beam. Then we have overhanging beams like this beam you can see, or in reality also in many places you will find this type of beams. So this overhanging beams means this portion is simply overhanging. Then similarly we have the number 4, that is fixed beam. So when the both ends of the beams are fixed, means embedded on a wall, like typically all the structures, maybe where you are sitting, it may be a multi-story building. So in that case the beam may be a fixed beam where you are sitting. So when the both end is fixed, then we call it is a fixed beam. And then we have last type of beam, that is continuous beam. When the beam is continuing with two or more than two supports, then we call it is a continuous beam. And then we discussed last class also the different types of loads acting on a structure or acting on a beam. It is a concentrated or point load. Sometimes load will be acting as a single point load. For example, if a fan is hanged here, for example, let me draw it quickly here. So yeah, so if you consider a ceiling fan will be there, right? So ceiling fan, something like that, it is hanging in this position, then this also will be acting as a point load, concentrated load or point load is acting in this point. Similarly, beam may be subjected to UDL also, like uniformly distributed load. And just like roofing, so we use tiles for our roofing, right? So tiles, sometimes we call it as uniformly distributed loads, are uniformly distributed across the surface area. And then we have uniformly varying load, means loads are varying from one side to another side. If you see, it is a triangular shaped load, and load is lower at this end, but the load intensity is maximum at the other end. So these are the basic three types of loads, but in reality the loads are much complex, like it is a combination of all three. So a load may be in any complex form. So in that case, basically we have to find it out the bending moment and shear force diagram. So that is our main objective of this lesson. So analysis of beam, basically we are doing, basically we are finding out the shear force and bending moment diagram. So in the last class we have seen this example. This is a simply supported beam and the only concentrated load is acting, that is a 10 newton and 1000 newton, and which is acting at the center of the beam. And we computed what was the bending moment, and we have drawn the bending moment diagram also in the last experiment. So in this experiment we will be more focusing on the shear forces. Okay, so the same beam, let's consider. So here I have tried to solve two beam. Okay, one is this one, that is simply supported beam with a concentrated load or point load at the center, and second case we have considered a uniformly distributed load. Okay, so let's see the first case. So when the loads are acting concentrated load, so first we computed what is the reaction RA and RB. The vertical reaction means it is easy to compute as the structure is very symmetric, so no need to write the equilibrium of equation even. So total is 1000 kilonewton acting downward, 1000 newton is acting downward. So obviously half of the load will be coming to this A and half of the load will be coming to this B, because this load is acting at the just middle point of the beam. So this is 500 Newton reaction, 500 Newton reaction, RA and RB. So once we know the reaction, then we can simply find it out the shear force. So shear force at different sections, shear force may be varying. So shear force can be computed either you consider the left hand side of the section or you consider it right hand side of the section. So here if you take a section and we are finding out what is the shear force at this section, then it is better to use only left hand side, because left hand side only a single force is acting, right? You can consider right hand side also and compute the shear force at this point. Both value will be same, but right hand side there are two forces, right? One is the concentrated load, another is the reaction force. So it is always better where the loads are less and simple loads are acting. So left side if you see only single load is acting 500 Newton. So the shear force at this point will be simply Ra, right? So at this point if you see only single force is acting which is vertically upward, so Ra, so shear force at this point will be simply vertically upward. Now if you consider this section at this point, so in the first case we have written that shear force at this section will be simply Ra, right? Now if we consider this section at this location, means after the load, after the concentrated load, then what will be happening? Then it will be simply if you consider the left hand side force, so we have two force, one is Ra acting upward and the P load or the 1000 Newton load is acting downward. So that's why Ra, which is acting upward, minus P means because the concentrated load is acting downward, so that is the right side. If you take the section right side of this concentrated load, then this is the equation for the shear force. Okay, so this is a very simple case we have discussed here. Now let's see a concentrated load, or sorry, a uniformly distributed load. So the same thing we considered, it is a uniformly distributed load, W is acting on it, and it is simply supported on two supports, A and B. So if you find out what is Ra and Rv, so it is very simple because this structure is also very symmetric structure, right? So in that case, Ra and Rb will be how much? So let me do it here. So total, how much force is acting downward? So total W for total UDL is W per unit, means total load acting downward is W, is in single unit length, but total length is here L, right? So WL. So total load acting downward is W into L, WL. So if you replace this entire UDL by a single concentrated load of which is acting at the center, then the force will be W into L, right? So W is unit per length, W per unit length. So here total length is how much? L. So that's why the total load acting downward is simply W into L, WL. So now it is a symmetric structure, right? So half of the load will be coming into A and half of the load will be coming into B. So what will be the Ra then? Reaction at A, Ra will be very simple. It is WL, is total half will be coming into Ra and Rb will be remaining half, it will take care, WL by 2. So this is the Ra and Rb for this beam, very simple beam. Now if you draw the bending moment diagram and shear force diagram, how it will be? So bending moment diagram, if you want to compute at the C, at the center point, what is the bending moment? So for example, we don't know, so let's compute that quickly. So mx, so we are finding out bending moment at the center of the beam C. Then moment at C will be how much? So there are two forces, right? One Ra is acting, which is clockwise direction, Ra is acting moment. So Ra is the force acting, and how much is the distance from the C? So from C to A, distance is simply L by 2, right? Total is L, so half is L by 2. So this is the moment. Force into distance is moment which is acting clockwise. So let's consider clockwise moment as a positive. That is our sign convention. Okay. So now another moment is acting, which is nothing but this UDL. UDL is also acting in this zone. So that value will be how much? So this entire zone. So we are finding out the moment at C at this point. So the entire, so one force we find it out Ra and distance is this much. So which is nothing but L by 2. So that's what we did, Ra into L by 2, which is clockwise. That's why we consider it as a positive. And another force is acting UDL, right, up to C to A. This is a UDL acting downward. Okay, so that downward force, now if we replace this from this portion UDL into a point load, what it will be? So the point load will be W is a unit load. So if you replace this entire UDL into a single point load, then what will be there? So total unit weight is W into total distance. Distance is L by 2, right? Half we are finding out. So up to C, basically up to this portion we are finding out. So it is W into L by 2 is a is the force which is acting again clockwise direction, anti-clockwise direction. So if you see, this is the direction anti-clockwise. So then the moment mx will be minus, anti-clockwise means minus, and the force is now WL by 2. This is the force, and the distance is how much? So whatever this distance, so this distance will be simply L by 4, right? So multiplied by L by 4. So if you simplify it, what is the value of RA? RA value already we computed, right? WL by 2. So WL square by 4 minus WL square by 8. So if you simplify it, you will get it WL square by 8, right? So that is the bending moment at the center, C. Bending moment at the center of the beam. At this location we have find it out. At C. That is WL square by 8. Now if you see, this is the bending moment diagram. Okay. And what is the maximum bending moment at C? WL square by 8, right? Just now whatever we computed, same value is written here. That is the maximum bending moment. Now if we write in terms of x, so we have derived at the middle, at the center point, that was the moment. Now if we find it out, what is the moment at a distance of x from the left hand side support, then what will be the mx then? So very easy to compute, simply same procedure will be continuing. So let me write it here. So mx, now at a distance of x we are finding out. This was at the center, mc. Okay, so mx will be how much? So reaction, you have Ra into x minus w into x by 2. So if you simplify it, you will get Ra x minus wx square by 2. How we got it wx? So w is the UDL is acting over this point, and we are taking a section in a distance of x. So the total moment is how much? Total load is how much? W into x. So that's why W into x is the total load multiplied by distance, CG distance, where the load is acting. So load is acting at the center, right? W at the distance of x by 2. So that's why multiplied by x by 2. So this is the equation mx, that is moment equation for this beam. So if you see, this beam equation is what? It is a quadratic equation, right? X square is there. So it is a quadratic form of equation. That's why if you see this one also, it is a equation of parabola, right? Equation of parabola, y equal to y square is equal to 4ax. This is the equation of parabola, right? Similar thing here also. That's why this curve is nothing but a equation, I mean the parabolic curve, this one. Because the bending moment diagram here also, if you see, it is a parabolic. X square is there. So it is a parabolic equation, so the moment also you will get is parabolic. So now, and the shear force diagram also, how we can compute it is very easy. So RA value is how much? We computed WL by 2. So at A, we have WL by 2. Now when you go from left to right, basically UDL is acting downward. So that's why the force is now, the net force is reducing. At the center point, you will have the zero shear force. Then again it is coming negative. And when it reaches to RB, again we have the plus WL by 2. So this is the shear force diagram for this beam, and this is the bending moment diagram for this beam. So although this beam is very simple beam, that's why we could do it in our hand. But in reality, if you see, the beams are very complex. It is in reality there will be multiple beams, and the loading also won't be simple, right? Here, so here the loading is very simple loading, and that is UDL. But in reality, the loadings are very complex. So that's why anyway, that's why we need to write the code, Matlab code or any code. Is basically we have to do the process, automate, and we can get the shear force and bending moment diagram. So here if you see, now we developed the equation mx equal to Ra x minus wx square by 2. So this equation basically we have to put it in the Matlab, and then we'll get this type of diagrams. So now let's go to Matlab and do the problem. So Matlab is here open. So very simple code, whatever we have discussed in the last class, that only we are following here, the same code. So basically we here first case was the concentrated case, and second one is UDL. So let's me do it for first concentrated case. So now simple shear force diagram, whatever we have done here, like this beam, this is a simple beam, right? So what is the shear force equation? So shear force equation is for the left hand side. If the section is left hand side of the concentrated load, then we'll have this equation. If the section is right hand side of this concentrated load, then we'll have another equation, right? So basically these are the two equations that we have to do it. So now this is a simple same code is written in MATLAB. So clear CLC, we have to write it as a default. Clear means it clears all the variables in the workspace, and CLC means basically it clears the screen. So now our command window is clean here. So now we just initiated with some value. P is a concentrated load, for example 100 is given, and X is where the section is. Okay, so here for example X is section is 1 meter, but in our problem we consider it X as uh, a 3 meter. Then L is the total length of the span, which is 10 meter, and Y is 6 meter. So what is Y? Y means at that location basically we are finding out the uh, shear force. So so X is basically where the concentrated load is acting. So here concentrated load is acting at the center, right? 2. So, but in our case, whatever you consider it, X is 3, where the concentrated load is acting from the left hand side support, and Y is basically where the section is, where we are finding out the shear force, that is Y. Okay, so now we have RA and RB computation. Simple, we discussed in the last class also in details how to compute RA and RB, which is nothing but simple P into L minus X by L. How we got it? We have used equilibrium of equation, and we find it out RA and RB, and then we have to write a condition, right? What is the condition? Because we have two equations here. If our this section is left hand side of the concentrated load, like whatever is shown here, then we have this equation, right? Vy equal to Ra. But if this section is right side of this concentrated load, then we have another equation. So that's why we need to write the if condition here. So if X is greater than Y, what is X? X is where the load is acting. So load is acting at 3 meter from the left hand side support, and Y is where we are finding out the shear force. So obviously Y is higher, right? That means the formula will be used for our problem is this one, that is the right side of the load. So the section is at the right side of the load. Okay, so now in that case, so if X means the load is greater than where we are finding out, then we'll have this equation, and in other all cases it will be Ra minus P. So same thing whatever I have written here in the slide, same thing is written here also. So very simple code. Now if you execute it, it will give us what is the bending moment, what is the shear force at a distance of 6 meter, okay, from the left hand side. So this is a very simple problem. I've written it. So now if you want to plot a shear force diagram, so how it will be? So now this plot we want. So this is a shear force diagram, right? Here I have not drawn anyway, but shear force diagram now let's draw it here. So the considered same value, some 100 X value is means where the considered load is acting, which is 7, and the L value is total length of the beam, and then our section is moving, right? Because here we have to find it out the shear force diagram, means along the all lengths we have to find out what is the shear force. So in last problem our section was static at any particular location, but if you want to draw the shear force diagram, then our section also has to be moved from left to right gradually. So at the first instant our section is just above the A. Now in the second instant maybe the section is above here, third instant axis is here, fourth instant axis is here, fifth here, sixth here, like that. Maybe we have to do multiple iterations, and at a different point. So if the section moves from left to right, at every instant you have to find out what is the shear force, and then if you plot it with respect to x-axis, then you will get the shear force diagram. Very simple. So now here also what we did, so our section now we changed from 0 to increment 0.5 to L. Okay, so let me clear the screen. So now if you see all the workspace is cleared now. So now if we execute first few lines, you will see what is P. P is nothing but the force, right? Total how much concentrated force is acting, which is P is 100. Now we have L. L means total length of the beam, and then X means where the load is acting. So now where is our section? As I mentioned, our section has to be moved from left to right, right? So there will be multiple sections. So yi is basically a vector which creates a multiple instant of section, means how sections are moving. So if you see, yi has total 21 values. So first value is 0, second value is 0.5, third value is 1. So like that it is moving. So at the first iteration we'll find it out at section at 0 what was the shear force. Then in the second instant we'll find it out when the section is at 0.5 meter what is the shear force. Then in the third instant, we'll find out when the section is at 1, what is the shear force. So basically, whatever earlier that simple cases we have run it, right? That is for the single case. But the same script now has to be run for multiple y value. So that's why we need to write a loop. Loop means basically it will the loop will run until and unless the conditions are met. Once conditions are not, once consider conditions are did not met, the loop will be simply going out. So anyway, so here we have to write a for loop, right? In for loop, how many times it will be running? It will be running total of 21 times, because in y1 we have 21 values, right? So this loop has to be run for 21 times because we need 21 different values. So now what I have written, I is a variable for the loop I have initiated. I is equal to 1, 2 colon means 2 length of y. So length of y means what? So if you just simply execute length of y, you will get 21, right? So length of y is 21. So 1 to 21. So entire loop will be running for the next 21 times. So when I value is 22, then over, section is just failed. I mean, the loop will be simply failing. So now at first instant y, because when the beginning the loop starts means I value is 1. So y value will be also y1 I means 1. At the first instant it will be 1. So first value, whatever yi values are there, so at the first loop, so y value first 0 will be taken, and it will compute what is ra, rv, and if the condition whatever I have written in the last slide also, if x is greater than y, then this is a shear force. If other case, this is a shear force. Over. So very simple code is written and it will generate the, and at last we are basically plotting yi means total how many sections we have with respect to y-axis is total all the shear force values. So now if you execute this program, you will get a plot. So yeah, plot has came now. So you can see this is a simple plot of shear force. So at the 0 instant, shear force is 30. Then if you see, so actually here shear axis is passing, and actually the line is passing here. Then at this point, it will just change the sign, and then again it will go at 0. Again it will go to 0 at 10. So this is the shear force diagram for this beam. Okay. So now this is the in loop. If you want to run it, then what will happen? So basically we have to write a the shear force basically we are writing in a loop, right? So that's what I have shown. So now, and this is a function. So if you want to use shear force every time iteratively, then it is easy to use a function, right? Last lecture also I have discussed about this slide part. I mean the function part, how to write a function. So very simple. I have written a shear force function, which it will take p, l, x, and y. These 4 values it will take as an input, and output it will give as a shear force. So whatever simple code, simple shear force I have written, same thing I just made it inside the function. So next time no need to write, if you want to find out shear force for concentrated load, next time no need to write the entire code, just we can call the function, and the shear force will be simply computed. So whatever I have shown just now, it is a simply concentrated code case. So here I am discussing two forces, right? Two cases. One was first case, this one, and next one is UDL. So whatever I have shown here, that is for the concentrated case. So whatever loading will be there, but if it is concentrated load, then we can use this formula and this script also. So now let's check it for the UDL part. So for the UDL also, what is the equation here now? So if I go here, so what is the moment equation for UDL? So moment equation for UDL is RA into x minus W x square by 2. That is the moment equation, right? So moment equation is same thing I have written here. See, RA into x. So here it is basically y, means where the section is there. So W is UDL, L is total length of the beam, and y is where the section is. Section is, for this example, it is given 5 at a 5 location. So RA and RB we computed. What is RA? RA already we know, WL by 2, right? So WL by 2, RA, RB also same value. So now MY is simply RA into y minus W y square by 2. So same thing here also, it is the RA into x minus WX square by 2. Same thing, but here x is instead of y. So this is a moment, and shear force is simply force, reaction force minus UDL, right? So shear force will be what at the distance of xx? It will be total forces, right, at this left of the section. So we have two forces. One is Ra is acting upward, so Ra minus, because UDL is acting downward, so Ra minus UDL is simply W into X. So that's what is written here, Ra minus W into X. So here it is Y. So it is a very simple UDL code. Now if you run it, you will get it, shear force, bending moment. So because here we are finding out at the center, right? So our section is at the center. So total length of the beam is 10 meter and our section is at the 5 meter, means just at the middle, right? So middle means what? So shear force will be how much? So if you see the plot also, so this is the shear force diagram, right? So at the center, how much will be the shear force? It is always 0 at the center, right? And bending moment is maximum at the center, which is WL square by 8. So simply that's what we got it. So shear force we got it 0, which is correct as per our plan also. And moment we got it 125. So how we got it? WL square by 12. That is our WL square by 8. So that is our formula. So W is this one, 10 into L square means 100, right? So 1000 by 8. So 1000 by 8 is nothing but 125. Okay, that's how we can compute the simple shear force and bending moment diagram for the uniformly distributed load. So same thing also can be drawn, shear force bending moment diagram with the same plot. So same thing I have written here, but here the section, as I mentioned, if you want to draw the diagrams, means shear force or bending moment diagrams, then we have to move our section from the left to right. So we have so using this one, we have created a multiple section, and then we have run a for loop, same thing whatever we did last time also. So the for loop is running for total length of y, how many values will be there in yi. Up to that time the loop will be running. So yi value and the RB value is considered, and then my and xy. So total bending moment and shear force for each cases we are computing. Same thing. Now we are plotting bending moment and shear force in the same diagram. So plot x is basically y1, and my is what? My is the bending moment, right? Bending moment. So we are plotting bending moment diagram, and hold on means basically in the same plot we are plotting another parameter, that is the shear force diagram also. So this hold on option is basically it will hold the earlier plot. Okay, if you don't give hold on, then in the two different plot, one will be bending moment, another will be shear force. But if you give hold on, then earlier plot also will be preserved, and in same plot you will see that both the figures. So now if you run this code, what you get it is W, some error is showing. Yeah, so here it will be actually W because we have used W. So let's replace it with W. Now let me run it and check if any error is there. Yeah, now there is no error. So if the program has run, and you can see this first one is bending moment diagram, right? So bending moment diagram, whatever we have seen here, so this is exactly same, that parabolic shape. So here also we got it, the bending moment diagram. And what about shear force diagram? Shear force diagram, how it will look like? So from A it will go up, then this triangular shape it will go down, and then again it will go up, right? So how much we got it? So at 0 it will go up, then we have this crossing part, and then again it will go to 0. So this is a shear force and bending moment diagram in a same plot, because we used hold on option, right? So this hold on option we have used, that's why both the plots are coming in a single figure, otherwise there will be multiple figures. So same thing also can be done. We can write a function also for that shear force bending moment diagram. Okay, and then we can plot it using loop also. Just here, see, just I have called the function here. So whatever shear force I have written here as a function. So entire code I have written it in terms of function, right? So now shear force is a function. So now every time if you want to call a shear force, no need to write entire shear force. Just call the function shear force and give the input parameter. It will give you the output parameter. Okay. Now if you run this, it will again show you the same plot. Okay, but here I have not called, I have not written the shear force entire program, but simply I just called it the function shear force, and which is this one. This is the function. Okay, so entire shear force code I have written inside the function. So that's what we completed our second or this problem, experiment problem, that is how to draw the bending moment and shear force for the UDL case also. Okay, so that's how we are completing this experiment number 9. So I would request everyone, please practice yourself, write the code and execute it, So the using the MATLAB, there is very huge advantage is that if you do some mistake, and everyone has done, everyone is doing mistake, first time or second time, whatever. Even if you are expert, also you will do some small mistakes. But the using this MATLAB is very useful because it will give you very good debug information. So you can see the error message and easily you can understand where you done the mistake. So that is the beauty of the MATLAB also. So this is concludes our experiment 9. So in the next class, that is experiment number 10, that is last experiment of MATLAB, we'll be discussing about the deflections of a beam. Means once the load applied on a beam, how much deflection will be taken place in a beam. That we'll try to do it and we'll execute it in the MATLAB. Thank you.